In this segment, we're going to talk about a proposed method of analysis for understanding the behavior of large language models and their ability to do in-context learning. And specifically, this is a mechanism called induction heads. So there's a kind of theory around transformers and their computations that's been developing that looks at basically what sorts of computations happen when you start kind of putting multiple attention heads and feed-forward layers, et cetera, together. And this analysis is broadly in the vein of what's called transformer circuits. And there's work by Catherine Olson et al. That looks at trying to understand how mechanisms like in-context learning emerge based on the kind of capabilities of transformers to do pattern recognition. So what they're trying to do is establish a causal relationship between the emergence of attention capabilities or surrounding this stuff and the ability to do in-context learning. So let's take a look at their experiment. So the idea of induction heads is that this is a pair of attention heads in different layers that are going to work together to complete patterns. So what we have here is a sequence of random tokens that then gets repeated later. So it's very much like the sort of text degeneration, like stuff's just getting repeated and the model is just happily going along and copying things. But why is it able to do that? Well, they claim that there's a pair of attention heads that enables this behavior. And the first one, which we're not really showing, is a head that just copies information from each token into the next token. Okay, so now the instruction token kind of knows about the word node here. Now, later on, when we're repeating the word node, that enables node to attend to struction. And what that means is that, remember, in the transformer, the self-attention computation is ultimately going to lead to some kind of vector, which is going to lead to some kind of prediction here over the vocabulary. And maybe the thing that gets predicted to come next is this struction token. So the fact that the model can look back and identify using the attention mechanism struction is going to allow it to predict that as coming up next. So this kind of suggests the same sort of idea as is happening in in-context learning. In in-context learning, you get these examples, of these pairs, X followed by Y, followed by another X, followed by another Y, showing you your label training data. And if the model is able to say, oh, okay, I'm going to associate what I'm seeing now, my input X, back with a previous label Y that might be the label, then that's a sort of almost nearest neighbor way of making a prediction about what that example should show. So we're still very far from a kind of full account of how you go all the way from data and the basic transformer operations to this sort of capability, but that's the idea that this is going after. So what they do here is they look at basically modeling these long sequences of tokens, and they're going to look at the loss of certain tokens and kind of characterize that. And they're going to associate models over time based on the patterns of their losses. And in particular, what they do is they look at the loss of the 500th token minus the loss of the 50th token, which they call this ICL score. That's the ability of a model to do a better job of modeling things later in a sequence because it's able to recognize that the stuff there is repeats of earlier stuff, right? So if both of these losses go down, that just means the model's doing better in general. But if the loss of the 500th token goes down a lot and the 50th token only goes down a bit, that shows that there's a lot of this in-context learning happening. Okay, so the kinds of things they look for are patterns like this, where on the left what we're seeing is basically loss. And they find that if they have a two-layer network or two or more layers, there's this kind of big drop in the loss where the model seems to be able to eventually figure out, kind of crack the code and recognize these patterns and model them with low perplexity. Then on the right, what they have are various measurements of the emergence of induction heads. And the claim they're making is that this improvement in the score for in-context learning correlates with when the induction heads emerge, and that starts to give sort of causal evidence that the induction heads might be causing this decrease in perplexity. Now, this doesn't actually show, there might be some kind of shared cause that's causing both of these things, right? So it doesn't actually prove causality. So they try to do some additional experiments where, for example, they change the architecture to promote induction heads developing faster, and then they find that this phase change in the loss happens even earlier. They also remove induction heads and see if they can kind of reduce the model's ability to model this. And indeed, what they find is that if you do that, you're able to change the profile of what you learn and kind of reduce the changes in loss that you were seeing previously. So I think this is a very interesting direction to explain why in-context learning works. It doesn't do so from a kind of theoretical mathematical point of view, but it's this very sort of empirical, like let's pull apart the elements of the transformer and figure out what's going on. What I'll say is that at least as of now, I'm not aware of any developments where this kind of understanding has directly led to, okay, we're going to change the transformer in this way, and that's going to impact how we want to train GPT-5. However, I'm not saying that this knowledge isn't valuable. So it's one of several avenues sort of studying these things theoretically. This is a vein called mechanistic interpretability, which is trying to understand these mechanisms. And then finally, there's the kind of fully empirical way of just saying, well, okay, what works and what doesn't? How do we prompt these models and get them to work well? How do we kind of understand over multiple trials what sorts of things work and don't work? And we're going to talk about that more later. That's the end of this segment.